I'm specializing mainly in analog and mixed signal, SERDES and signal integrity from MathWorks. So this topic is highly relevant and I often receive inquiries about how MATLAB can aid in the design and optimization of mixed signal ICs, the integrated circuits with MATLAB. So therefore, we decided to share a set of tools to help you achieve how you perform this kind of optimization. So the growing complexity of ICs has sparked significant interest in mixed signal optimizations. This complexity is driven by factors like smaller circuit sizes, enhanced functionalities, faster speeds, reduced power consumptions, and more compact processors with greater variability. So additionally, tighter integration necessitates the correction and also we need calibration of parasitic effects. In general, the traditional techniques are often inadequate to manage this complexity, whereas we use a many computer aided designs which help us to do this optimization and makes the engineer life bit easier. We get beneficial using this computer aided design tools. So it aids the designers by offering behavior level models for early verification. You can employ various optimization techniques and utilizing statistical methods for experimental designs. You- Nowadays, we know AI is booming and AI can also be leveraged to tackle particularly the challenging problems or those requiring extensive data analysis. MATLAB provides tools in these specific areas to support the integrated circuit design. So today, we will be focusing on how we perform this optimization of the mixed signal ICs and how that can be done using incorporating AI in it. Before that, getting into the optimization, how a traditional design workflow is being done, like how an integrated circuits are being designed. So these integrated circuits are being developed by the semiconductor companies, like many semicon industry people. They get started with the spec, and then they go with the algorithmic or the architectural exploration. Either that could be a digital design or an analog design and a mixed signal modeling. And after doing the algorithmic designs, we try to implement that in the software or in a hardware. And sometimes we use a verification system verilog code generations for the verification aspects. And finally, we end up with deploying that in any FPGAs, or we also end up with an ASIC modeling. So we go with a different waves, like either creating an ASIC complete ICs, or we go with the deployment of FPGA models. And this is how the traditional workflow is. So here we would be mainly focusing on this part, what we call it as the system level modeling or the behavior level modeling. So in this, how we perform the system level modeling or a behavior level modeling. We design, simulate, and analyze the analog and mixed signal systems both in time continuous as well as the discrete signals in the time domain. We perform the system level designs like PLLs and the data converters, where we design and provide the spec to it and analyze it using the test benches and measure that if we go with a phase noise measurement, or if we go with some kind of INLs and DNLs, and if we want to add some kind of an impairments to the model, we do add that and get the results out of it. Where we work on a signal flow modeling and we visualize and find the results using the plots. So here you get started by making use of the system level modeling, like you design your PLLs or you design your data converters, you go with the clock generation, and that can be used in a different application. Similarly, we get started with the analog to digital converters, where it can be used for sensor data acquisitions, and it can be used in digitizations of data. So all these things are get started with first going with a system level modeling, and then analyze the results and find that yes, it's working fine. Then we go with the circuit level modeling, and then we end up with the final tape out. So this is a traditional workflow, and we first going to discuss on the system level modeling, and also when you go with your circuit level models, how you get that data and how you perform the post processing. So that would be the main discussion of today's presentation would be. So IC optimization can refer to various processes, and today we will explore two types. First, we will discuss on design optimization, which occurs at the transistor level during silicon design. We analog design engineers, we go with first, we'll go with the transistor level modeling, and there we face some kind of a challenges and how we do the optimization over there. That would be the first discussion. What would be we discuss over here? This involves about adjusting the transistor sizes, and we can also minimize the layout parasitic effects, the power consumptions, area, or the speed. So the next second type, or the second topic what we would be discussing is performance optimization. First, we will be discussing on the design optimization, like how we optimize the transistor sizes. The next one is how we are going to work on the performance optimization, which takes place at the architecture level or the algorithmic level. So this optimization is executed at runtime. When you are running that simulation, this kind of an optimization runs during that runtime or during your calibration time. Examples includes like when you're working on the adaptive equalizers, or when you're working on linearization algorithms, calibration circuits, or when we are working on the PVT, when we say power voltage temperature variations. So using these optimization methods, we can actually perform the design, and also we can increase the performance as well. Yes, we are also going to, when there is optimization differs, we also end up with some kind of common challenges which will be looking going forward. So when undertaking these optimizations, we need to address the following questions. So what is the objective function? What ultimate goal are we going to aim to achieve? So, is there any specific metric do we want to optimize? Or what variables can be adjusted to meet our objectives? So, is there any kind of a limitations and acceptable values for these variables? When I say variables, for example, if I take a transistor sizes, I would be considering what should be its width, what should be the length, what should be the bandwidth, what is my passive components, what is the variable ranges it should be, and how these are what kind of a limit I need to go with. Without any defined problem scope, you might end up with impractical solutions. So like you can go with the capacitor size, which is very, very, very larger. And also we need to consider what additional constraints we must be looking for. So if you want to reduce the size of an IC but still need to maintain a specific gate or a bandwidth, how you can do that. And similarly, which optimization algorithm is suitable. So to get started with an optimization, when I say optimization, it's nothing but how what the best values which you can use for your design to achieve the best results. And before going into that, I need to see all these constraints, like what are the things I need to consider before me performing the optimization for my mixed signal IC. So with that, we are going to see two examples today, and we are going to start with the first one where we optimize the design of an operational amplifier. Here, As I mentioned earlier, we are going to look into two things. One is a design optimization, another one is the performance optimization. So the first one, we are going to look into the design optimization. We are going to optimize this circuit, what you can see in the screen, which consists of fewer than a dozens of transistors. It's a very basic model. I'm not going with a very larger circuit. It is just having a dozens of transistors, making it a relatively straightforward. So this example will serve as a guide for you to go with many more complex systems. So this would be a getting started one. So the first step involves identifying the variables, boundaries, and the valid values for optimization. Here we have chosen the transistor sizes, which you can see here, the width, the length, and also the multiplication factors. Some transistors are paired in a mirror configuration, so certain variables are interdependent. Notably, the transistor length can only be adjusted in increments of like zero point 0.1 micrometers, turning this into an integer optimization, turning into an optimization problem rather than a continuous one. So the second step is identifying those constraints. What are the metrics? In this case, we have bandwidth, current gain, slew rate, and unity gain bandwidth. These metrics are derived from the transient AC and the DC simulations of the circuit. We can set these constraints. So these are the metrics which we considered. So for instance, if we want the 3 dB bandwidth to exceed 2 megahertz, or we assign a weight from 1 to 100 to indicate its importance in meeting this constraint, we use these weights to combine constraints and assign whether we meet these targets. What is the third step? Our third step is based on a simple observation, performing a brute force analysis by simulating all possible values combinations. Like we'll go with all possible values of the transistors would require over 10 million or even billion of simulations, up to like around 1.3. You can just see here up to 1.3 e power 16. So this approach is not feasible, right? Going with billion of simulations and going with observing that what kind of combination of transistor values can be provided. So instead, we use a surrogate optimization method, which builds a surrogate model of our circuit to reduce the number of simulations while still finding the optimal design. And the fourth and the final step are quite straightforward. We run the simulations and apply the results to our IC design. This process can repeated iteratively. So for example, if you are exploring different constraints, goals, or break down the problem into similar issues, smaller issues. So we will be looking each and every step in practice going forward. So in order to perform the optimization of your transistor sizes, these are the 5 steps which you'll go forward with. First, define your variables, and then second, set up the metrics or set up the constraints. Third, instead of we doing it n number of simulations, we are going with the surrogate optimization method, run this optimization, and finally end up adding these optimal values to your IC design. So if you see here, I have added a video just to show you about. We are opening up the Cadence database here and the test bench for our op-amp and the master view. Right here we are in the Cadence environment, and we are talking about the op-amp design. This is a top layer, and we are talking about how we have a supply, a bias generation. We'll look one layer into it where we see the schematic of the actual op-amp with the transistor implementation. We open as an assistant the variables and the parameters we can want to verify how different we can go with the variables for the transistors. And the transistors which are mentioned at the side you can look into what other transistors, and certain transistors would be coupled. For example, we see that the transistor 24 and 18 are using the same variables. So this is a transistor 18, and you can see here on how you can use the same variables as of 28. In this case, we see that 27 and 25 use the same variables. So matched transistors essentially have the matched design variables. So this is how we set up our problems, and this is the problem what we want to resolve here. You see also here on the left side of your panel, the variables with the bounds and the steps what we are going to define. In the middle, we find the metrics, and the metrics are determined based upon your transient AC and the DC simulations. You can see that we define the bandwidth, the current gain, and the relative specs with the constraints. So for this example, what we are thinking is we will be having the gain greater than the 35 dB, and as well as the relative weight in case of around a weight of 100. So this is how we set up the problem in Cadence, and we just run the simulation. So in the next 10 minutes, we will also going to see how we use the MATLAB, how we can help us in automatically scaling these dimensions. So here we take these values, and we also mention the dimensions of the transistors in such a way that we meet our constraints and our optimization objectives, so that when we apply this computed width and length multiplication factors, we actually meet all our specifications. But before diving into our optimization problem, let's take a step back, and we actually see that whether we are looking at our design parameters, right? So here I'm going to just sweep the variables, and that is the width and the length of the transistors, and we are going to increase the step over which we will be performing the sweeping of all the values. We can go with 304 simulations, which is like we want to achieve the target. So this is already useful information because it gives us some idea about the sensitivity of the circuit. From here, we can invoke the MATLAB directly from the Cadence. You have seen from the Cadence master environment, we have opened the MATLAB environment, and the data might be coming up in the form of ADE info, which you have seen at the right side over here. Once if you get that data directly into the MATLAB environment using the mixed signal analyzer, I'm fetching that data, and you can see that data at the left side over here. I'm so from Cadence environment, after me performing the simulation, I have got that waveform data into my MATLAB environment, and whatever the waveform data you have got, that comes in your left hand side. And here for that particular data, I can plot the results, and you can look into the plotting of, you can see this is the gain for this transistors. And this is again, so there you can actually find the n number of cases which we have put up, where you can see the width over the x-axis and length over the legend. We can have multiple categorical axes with this view, and we can also see how essential the gain has a fairly smooth trend over the width and the length. There is a different trade-off which is happening that provides a maximum gain, which you can see at the right hand side here as well. So this data, whatever you can see here, which is being taken from the Cadence environment. You can plot your gain, you can plot your slew rate, and here I am plotting the trend chart of the data what I received from the Cadence environment. So what I'm trying to say is you can also cross probe the curves. You can set the data to identify the specific data points, and the similar way you can plot all the gain, the slew rate, and also you can go with the unity gain bandwidths. You can also compare these behaviors. You can see the top one and the below one. You can compare those behaviors next to each other, and you can also look into the trade-off between these behaviors. So till now, I just showed you about first thing how you start with a cadence environment, and from there how you go with the simulation, and from cadence itself I will be specifying what are the variables which I'm going to optimize, and after selecting those variables I will invoke MATLAB directly from cadence, and from there the MATLAB will get all the data which was simulated in the cadence environment, and for that data you can do the plotting and all that stuff. But before you start, or before we begin with the optimization, we first access the sensitivity of our integrated circuit, right? So this involves examining a limited set of design variables or configurations, and using MATLAB we analyze and identify these key trends. So this process helps us to understand which metrics are important. Like for example, I need to understand if I change this metrics, how it is that changing the results, or how effective is that in my circuit. So this is a standard procedure for the designers. So as it provides a valuable insight in the overall system performance. So we need to understand this process, which metrics is important and which are sensitive to changes, such as if I change some variation in the transistor size or length, or which transistor most significantly impact the performance. However, this method alone isn't suitable for circuit optimization due to the impractical number of required simulations. So I have changed the values, I have bought that, and I'm doing the simulations, but this is very impractical because I'm not going to end up with billions of simulations. So it definitely need an optimization algorithm to make this a bit more effective. So how are we going to do this? As we discussed in the previous slide, there are 5 steps. The first step is, let's begin with importing the variables as defined in the cadence virtuoso. We will identify the independent variables. We will determine their bounds. And if only discrete values are allowed, we would be configuring the optimization algorithm for this integer optimization. We will use several helper functions, like utilizing the ADE info object to identify the independent variables and make them accessible in MATLAB as a lookup table. Right? We get the data in MATLAB environment and we will be providing in a form of a lookup table. For instance, for the first variable, we determine its name. You can see that we determine its name, and we make them the lower and the upper bounds. And these are the lower bounds, these are the upper bounds. And we all importantly, we will be providing the scale factor, right? Which dictates that how the variable sweeps over an integer set. So on whole, your first method is to read the independent variables and you're going to set up the environment, right? Mentioning what is my lower bound, what is my upper bound, what is my scale factor, and what is the parameter which I'm going to optimize. This is the first step which we would be doing. And the second step in our optimization problem is identifying this scale constraints. So that is our next step. So in Cadence Virtuoso, we have defined our set of constraints, right? Like we have set up like what the bandwidth. These are the metrics which we consider: the bandwidth, the current, the gain, the slew rate, with whether to be greater than or the smaller than the certain threshold value which will be setting it up. But what is interesting to observe here is that each of these metrics, they have a different unit. You look into this, each and everything is having a different unit and with a different scale. So for example, we go from current, that it is in the order of microamperes. When we go with a bandwidth, that is in the range of megahertz, so 1 into 6. Or if we go with a gain, then gain is in the range of dB. So we have constraints that have different ranges. When the optimization is performed, we need to determine how close we are to our goal, first thing. And for this reason, we need to scale the constraints so that they can combine into a single metric. As I said, each and everything is having a different ranges and different units. First thing we will be doing is we want to understand that how close we are to our goal, and for this reason we need to scale the constraints so that they are combined in one single metric. In other words, we need to build a single cost function where these constraints are suitably combined throughout the factor, that is the function of the value is the constraint and it is relatively weight, right? So in this example, we will need to combine very large properties such as bandwidth and with very small properties such as current and with something that is somewhat in between such as the gain. So we are considering these three parameters: bandwidth, current, and the gain. Additionally, we need to turn all the maximization targets into a minimization problem. This is because often optimization algorithms are looking for the minimum of the cost function. And to do this, we apply an inequality sign so that instead of maximizing the gain, we will try to minimize the negative of the gain. So that's how we are actually trying to consider the values. Since everything will be of a different constraints, we are going to make it like a one single cost function. So that is our second step. And now let's get into the third step. The third step of our IC design optimization is we configure our optimization algorithm. This is the main step. Like instead of me going with manually doing millions or billions of simulations, I would be using a surrogate optimization method. So which is implemented using here for this whatever we are talking about, we are using the global optimization toolbox where we begin with defining the objective function, right? First we'll be defining the objective function, or we call it as a cost function we aim to minimize, which is the one which we are trying to minimize. That's our first step. In this case, we focus on the gain. So if you see here, we focus mainly on the gain values and we include the scale constraints to establish our cost function. We utilize a helper function called getMetrics. So we are using this helper function getMetrics and we employ a function handle to pass this function to our optimization algorithm. So this is the function which helps us to get this information to the surrogate optimization algorithmic method. I'm so sorry. Just a minute. Cool. So here we allow what we are going to do is we are using this helper function getMetrics and we are passing this function to our optimization algorithm. What will it do? This allows us to adjust the design variables and it will help us to recalculate the cost function during the optimization process. So we select the surrogate optimization algorithm, a global optimization tool for its known robustness in handling non-continuous problems. If you see here, when we are trying to optimize the transistor sizes, definitely it won't be a continuous one. It will be definitely a non-continuous problem. It might be keep on changing. So this non-linearities, what we call it as non-continuous problems, need to be considered. And this global optimization or the surrogate optimization is the best one, which can be used to provide us the efficient cost functions or the efficient results out of it. Additionally, we incorporate a custom plot function to monitor the progress and we will be keep on looking into it. This optimization method will be doing n number of iterations until we reach or restart the optimization if it is required. So suppose for instance, if there are around 60 simulations, we can adjust the parameters and resume the last saved point for better controlling the optimization process. So till now we have seen three steps. The first step is we started with go, finding the variables, and second one is scaling that constraints, and third one we ended up adding the surrogate optimization method to those variables and doing n number of iterations to just get the best result out of it. And now finally we end up with the fourth step in our IC design optimization, which is simply running this optimizer. You can just see we will be simply running this optimizer. We execute the optimizer directly from the MATLAB environment. We are not going to go with the cadence again. From MATLAB itself, using this optimization method, we would be running the values in the MATLAB environment, and this will be giving the best results or the best values which can be applied to this transistors. So we call our surrogate optimization method. We provide the objective function as a handle, and we provide the lower bounds. When I say lower bound, what is the minimum value? What is the upper bound for our design variables? We also specify that the variables must be integers. So as the optimizer runs, simulation happens in the cadence, which will be happening in the background. So we observe the simulation being populated, and we can be keep on tracking our progress with a custom plot, which can you see here, showing that how close we get to the final solutions. So if you see, these blue lines indicates the best one values. So it will say how much amount of cadence simulations need to be done to get the best results out of it. And since we are controlling this using the MATLAB, we are getting the results very faster, and you can see the gain at your y-axis and the number of cadence simulations at your x-axis, and the best gain value was achieved after your hundreds of simulations. And this can be done in MATLAB environment, and that will give you the best results of what should be your transistor sizes and what should be your other passive components you have selected. And it will also say that you can see here these green values mention that the constraints whatever I have set, my gain need to be this, my bandwidth need to be this, my current should be this. So this green mentions that yes, it has been achieved with these values. So when I would be iterating, giving many values, and I'll finally ended up with one value, and that one value is achieving the results. My bandwidth, whatever I have set, is passed. My current is passed. Yes, that might be certain constraints which are failed. So that need to be focused. So I'll be doing reiterations again, and till I achieve the constraints, whatever I have set, I will be doing this process again and again. So this is the final step where we apply these results in the cadence environment. We run the simulation in cadence, and we need to verify that we met our targets, and we find that whether the design performs as we desire. If this is not actually done, then again I'll go and I'll do the optimization. I'll apply my optimization algorithm until I achieve my results. So this is the point where we can further elaborate our design. So with that, we have extensively seen about how we are optimizing the transistor sizes in the cadence environment, or we have conducted numerous simulations in the cadence virtuoso utilizing the M button. M is nothing but the MATLAB environment, which seamlessly transfer the simulation data into MATLAB environment. We activated the M button within the cadence virtuoso, specifically the cadence maestro view. So from cadence maestro view, we can obtain a variable called the ADE info. This ADE info will be having all the waveform data which we got from the cadence environment. And we also learned how to plot these variables. Like if I have a data, how I'm plotting this data using the graph, the plots what is available in this mixed signal analyzer. And similarly, there are inbuilt functions, like if I want to measure the phase noise, I'm just giving you an example. If I want to measure the phase noise, or if I want to go with the calculating the INLs or DNLs. I will just select this data. This is the real time data what I got from my Cadence environment, and with one click I will get the plots for it. And similarly, you can get one more data. You can just compare the results between each other. So on the whole, to summarize, you can analyze the waveforms, you can analyze the trend charts, you can compare the simulation results between two datas, and finally you can go with the reporting or document, like you would be going with a PDF or a PPT with all these plots. So everything can be done by making use of this mixed signal analyzer, where this cadence data will be taken, and for this data you would be doing this optimization methods. So here we enhance this workflow further. So starting from cadence, we activate the M button, and we created our ADE info object in the MATLAB workspace, which allows you to probe all the design parameters using the ADE get command. So what I'm trying to say is, you're once after you have designed everything in the Cadence environment, now you get the data in MATLAB and you can control everything from the MATLAB environment itself. So here you can use the ADE get command, and where you can actually reveal all the data variables in your Cadence design space. You can include the bounds, you can include the steps for variations. We transition from Cadence to ADE info and we utilize the ADE get. Next, if you want to modify these parameters, you can go with the ADE set function. So this is the ADE info which you get into the MATLAB environment, and you can, using the ADE get, you can get these data into the MATLAB environment. And using the ADE set, you can modify the values or the parameter values. And for instance, you can assign a specific value to your variable, which is directly applied in Cadence environment. So here, when I'm in the Cadence, I use ADE get to get the data. And in the Cadence environment itself, I'll use ADE set to set the values for this Cadence data. And similarly, I will use ADE sim function, which will be running the Cadence simulation also, right? So here, essentially what I'm trying to mention here is, MATLAB acts like a controller for the Cadence simulation. We import the data for analysis, we read it, we set the variable values, we run the simulation repeatedly in a feedback loop, which is how the optimization problem is configured. On a very short or in a very summarizing method, you can read, set, and you can simulate it in n number of feedback loops until you end up with the desired results. So this is all about the what we were talking about on the optimization or the design optimization. But I was keep on saying about surrogate optimization, but I just want to take or spend a few seconds to talk about the surrogate optimization method. So there are a set of techniques that are based essentially on artificial intelligence. So if you like, where essentially that are useful for solving problems where the cost function or the goal function is extremely expensive to evaluate. When we say extremely expensive, like for example, the cost function, when I say I want to achieve this gain, or if I want to achieve this bandwidth, and this is a parameter which is actually affecting this performance. So I need to consider those things, and I need to look and I need to reiterate it again and again such that it doesn't affect my performance. So the advantage of this method is that it uses fewer evaluations compared with the other optimization solvers. Even though, truth to be told, in the global optimization, you also find other techniques such as genetic algorithms, or there would be a pattern searches, or there are different techniques. But this method is actually help us. There is an advantage in it that it does not rely on gradients. So it works both on smooth as well as the non-smooth problems. When I say smooth or non-smooth, it is nothing but linear and the non-linearities as well. And it builds an essentially surrogate model that gets progressively improved. So this method is faster to compute, and you can use this for a full IC simulations. And this technique is very promising for complex circuits, far more complex than the simple op-amp that we just seen today. We just took an op-amp as an example, and in that op-amp we just took a couple of transistors, and we set up that I need to achieve this bandwidth, this is my gain and current, and I made the current surrogate optimization method, gave this input to that, did the optimization algorithm, and then finally I have implemented that in the model. But you might be having this question that why did you use a surrogate optimization? For that, I just gave an explanation saying that this method is very suitable for both smooth and the non-smooth problems. And this is a very promising algorithm which can be used for your complex designs. So with that, I'm going to go with the next optimization, which is the performance optimization. And yes, I won't take more time, but want to say that how we perform optimizations of mixed signal ICs. One, yes, we consider on the design side, but yes, we need to focus on the performance side as well. So our topic would be on how we improve the performance of your ADCs or the DACs, or if you're working on some kind of another mixed signal ICs. So here we are going to focus on the interleaved ADCs. So let's start by providing some background or some motivation on why this exact thing is being taken over here, right? So in general, modern high-speed digital I/O communication systems, they require faster and faster data rates, right? Nowadays, we go with very high-speed data rates, and this has been moved the architecture of many service systems to use analog to digital converters. So, however, the data rate is so fast and so high that a single flash ADC is not sufficient. For this reason, this type of architecture is frequently using time interleaved ADCs. Yes, earlier we were using the flash ADCs, but for very higher data rates, we might we are ending up, I could say we are ending up with the time interleaved ADCs. In this way, each of the ADC can operate at a slower data rate, sample rate, and overall performance is still, it is actually met by interleaving the results of each of the ADCs. So when we say interleaved ADC, you can combine the different ADCs. However, when you insert multiple ADCs in your receiver, right, the ADCs might be affected by slightly different impairments, and this happens, then the quality of the overall ADC is not the one what you desire. So we were talking about the performance optimization, how we end up with this performance optimization. Yes, for the higher data rates, we use the interleaved ADCs. But when I use this interleaved ADCs, each and every one might be having a different impairments. And when I go with the different impairments, that would be affecting my performance. So we will be using this one to explain you how important we accompany the analog and mixed signal systems together with the digital correction algorithms to compensate for some of the impairments. So here what we are going to do is, or what we are going to show is how this is can be done using the MATLAB and Simulink for many other mixed signal integrated circuits. So first of all, we will start by developing a behavioral model of our ADC. So you can see this is a behavior like a system level modeling of an ADC. And we will use this behavioral model to estimate the impact of the impairments. In this case, we will focus on the offset and the gain errors. So this will be created using the MATLAB and Simulink environment. And secondly, we will develop a correlation correction or a sorry, it is a correction algorithm using a system level model. We will experiment with possible architectures for the correction algorithm. At last, we will verify the performance of the ADC in the correction algorithm using the system Verilog models. So we will use this model transformation, how it can help in going from architectural studies, behavioral modeling towards the ADC implementation, right? So the previous example, we were talking on how we perform the design optimization, like going into the circuit level, and from circuit, how you get that into MATLAB and how you perform the post processing. And in the second method, we are going to focus on the performance optimization. When I say performance, yes, when I go with high data rates, definitely there might be a many challenges what I'm going to face, and how I'm going to improve that performance. I'm going to work on creating the system Verilog codes, and I will be using these models and how I'm going to go with the ADC implementations. So that is the three-step method what we are going to focus on. First, behavioral modeling. Second, developing the correction algorithm. And third, we would be generating the system Verilog models and how we use that for the verification of your ICs. So first method, we'll start by modeling the ADC behavior, accounting for impairments like gain, offset errors, and we will be taking those identical gains and errors across the four ADCs. With the sinusoidal input, we get a clean output, but spectral analysis shows a peak and the noise floor due to quantization errors, right, in our 8-bit ADCs. Next, a test bench isolates impairments to observe offset and the gain errors. So the green background, what you are looking into the image, it shows the gain errors causing noises and the spurious signals. So offset errors add noise and the harmonics at the sampling frequencies. So the gain and the offset errors contribute to different spurious components. Combined, they reduce the SNDR, and they are reducing the ADC to a 3-bit performance. There's the actually in this case you can see that the gain error has a 7.5% deviation, and also the offset error is 25 millivolt, highlighting their impact on the tolerance levels. On the whole, what we are trying to do is we are going to use the behavior level modeling, provide the spec to it, and using the test benches we are going to analyze it by adding the offset errors and gain errors and see the performance. We are experimenting it with random values and see the performance of it. So this is the first method of building or creating the behavioral model, including the impairments to it and verifying the results. What is the second method? The second method is nothing but creating a compensation algorithms to address the impairments introduced in each of the ADC. So our system level model for this algorithm includes several components, right? First, we have the ADC with gain and offset errors using the behavioral model which were developed earlier, which we saw in the previous ones. Next, we would be applying the correction algorithms. And the third thing is what we will be doing is first we have the ADC with the gain and offset errors. So here you can see in the green section, we apply the analog correction here. We would be applying in the analog correction, which removes the gain error while subtracting the offset correction at the ADC input, which will be removing the offset error. This process must be repeated for the interleaved ADCs. So over time, gain correction converges to 1 and offset correction to 0, indicating effective error compensations. So what we are trying to do is we will be having the ADCs and we are trying to add this correction algorithms in such a way that it will help us to remove the offset errors and it will help us to remove the gain errors which is being added in the model. So this approaches not only demonstrate the algorithmic effectiveness, but also provide hardware designers with a preliminary cost estimate of how you are going to go with the RTL implementation. It will tell you about how you can go with the modeling of your hardware itself. So the final step, as we saw, first step is modeling, second step is adding the correction algorithm, and the third step is ensuring whether the IC is reaching or whether it is achieving the results. So for this, we ideally call this as a verification. So the verification would be occurring at the transistor level, but that often takes too time consuming. So instead, a final verification can be done once the design is complete. So to build the confidence, we use the behavior level models. Specifically, we create or we generate the system Verilog models generated from these blocks. So here I have an interleaved ADC which I have created using the system level models, and these models can we can generate the system Verilog codes out of it, and these system Verilog codes can be used in any tool for your verification of the mixed signal ICs, right? So here these models can be integrated into your cadence environment, or you can actually provide as a reference to your IC development. So for the ADCs, manual design is necessary since synthesis isn't feasible. So a behavioral model will speed up the verification of your complete model. You can which can directly generate the RTL from Simulink, and you can create the synthesizable Verilog or VHDL, or you can use this HDL in your such as in your pre-developed IPs. So the Verilog implementation of the compensation controller is very effective and it is straightforward. We will integrate existing HDL with the system Verilog model from the Simulink for the interleaved ADCs. On the whole, you can actually do a behavior level modeling, and you can use the correction algorithms, and finally you can generate the system Verilog codes, and these system Verilog codes can be used for the verification of your mixed signal IC, and that's how we will be improving the performance of your design. So with that, I'm going to go with my conclusion of we have seen so much. I have said so many things today. We have seen a lot, right? We have seen how analog and mixed signal we can customize, we can use optimization techniques, how we can get the data from Cadence into MATLAB, how we can apply the global optimization, surrogate optimization method to do the optimization, design optimization of your transistors. We have also seen how MATLAB can help designers gain their insights within the data. Like you can go in depth and analyze, you can see the trend, you can use the methods of the simulation results, compare those results. You can develop the custom objectives. You can go with the linear and non-linear constraints. You can design how an analog mixed signal IC do its performance optimization, how we can do the performance optimizations, and all that we have seen here in this webinar. So to just give you a summarizing about whatever we have seen, first, we have seen about the design optimization. And second, we have seen into the performance optimization. Design optimization, where from your cadence environment or from your circuit level, bring the data into MATLAB, and there you use that data, have the bounds, and apply the optimization method and get the best results out of it. That's your first way of doing. And the second one is performance optimization, where you would be creating the behavior level models, adding a correction algorithm to it, and finally end up with generating the system Verilog codes where you can use that for your verification aspect. And now I'm at the last of presentation. You can ask me where to find this information. If you want to know more about it, you can look into these examples which are included in the mixed signal blocks. You can also try to implement at your end, and you can reproduce all the results, what has been demonstrated or what has been discussed over here. And if you want to get the access to this presentation, you can scan this QR code so you can get all the details, whatever has been discussed over here. And also, if you want to know more about this, there are the links which can be available where you can try at your end and get benefited. So that would make your life more easy. So with that, I'm ending my presentation. Thank you very much for your time, and thanks for joining this webinar.
Yeah, thank you very much, Janvi, for such an insightful and elaborate presentation. So really appreciate. So we have few minutes, and if there are any questions from the audience, kindly unmute yourself and you may ask your question to Janvi. So Janvi, while maybe audience is thinking, I have a question. So
Yeah, Sanjay.
this the sizing optimization of the analog
Mm-hmm.
blocks, right?
Yes.
So so it is required that first it should be a bit verified in the cadence to get some bound of the parameters or the transistor sizes and then go for the optimization, right?
Yes, that would be, I could say, the best method of doing it, because we know that we will be having a very complex models, right? The one which we discussed is a basic op amp, but when in practical we will be having a complex designs and the transistors, we want to understand which are those parameters which need to be considered, which is affecting or which is having a more impact on the design. So when I consider these things, and then if I take to the optimization, I would be looking into the best results, or I might be getting that. Yeah.
Yeah, makes sense. Yeah, thank you, Janvi.
Thank you, Sanjay.
Yeah. Any questions from audience? Okay, it doesn't seem any. So thank you once again,
Yeah, Sanjay,
Janvi.
this is
Yeah,
Samaksh.
yeah.
Hi,
Hi,
If you
Samaksh.
Samaksh.
allow
Hi.
me a
Yeah,
quick,
please,
yeah.
please go
So I
ahead.
think there is a question in chat, if I'm not mistaken.
Okay.
Okay, let me just have a look.
Shubham has a question.
Give me a second. In the chat. Okay.
So
Okay.
I
Yeah,
can see
indeed.
that how
Yeah.
to generate the lookup table by multivariable sweeping, like if I want to change the VGS, VBS, VDS in MATLAB. Okay, that's a wonderful question. So, uh, to tell you, as you said, I will always use the lookup table to get the data into the MATLAB environment. And I want, as you said, yes, I will be not doing just only a specific sweeping of only a particular voltage. I will be doing multiple variable sweepings. Yes. So how do you generate is it's the same thing again. You need to just fix that what is the variable you are going to consider in the MATLAB I mean the cadence environment, which just Sanjay mentioned. So I will be changing. I need to first fix what is my lower bound, what is my higher bound, and what is my scale factor, and what are the parameters need to be considered. And if I fix those values, and I can invoke MATLAB directly from the cadence environment where these values can be taken. I can also discuss with you offline in more detail about how you consider the multivariable sweepings. Hope that answered your question.
Okay, given that we are almost out of time, I just want to thank Chanvi you and thank Sanjay for organizing this. And at the same time, I would also like to share with the colleagues that MathWorks, the makers of MATLAB and Simulink, this is access. Most of the large companies in India, MNCs, have access to these products, right? So it's like the enterprise customer, they have the access to all of these products. So John, if you could flash that, yes, thank you. So if you have any more details, you can go and look through this. And I just wanted to close with that. And Janvi, if you have any last words, please go ahead.
Thank you. Thank you so much. Once again, thanks everyone for joining this webinar, and I hope it was useful. Any questions, or if you have anything, please feel free to reach me. And this you can just scan this, where you can get all the details of this presentation, where you can find the mail IDs as well. And thanks, Sanjay, for coordinating this, and thank you so much.
Thank you very much. And just to mention that this recording of the presentation will be posted on the IEEE SSCS Daily Chapter YouTube channel. So people can go there and refer. Thank you very much, Janvi and Samaksh, and have a good day. Thank you. Bye bye.
You too. Thanks. Thanks,
Bye.
everyone. Bye bye.